Hey class, and welcome back. What I wanted to do with this video, since we're not going to be able to be together for class on Friday, was wrap up the last couple ideas from Chapter 1, Section 2, and then introduce you to some of the concepts around work and energy as we dive into the last section of Chapter 1. So, the last question that we talked about just briefly at the end of class when we're talking about motion of an object was, does a ball's horizontal motion affect the way in which it falls? And as we saw in the demonstration I did at the very end of class, the answer to that is no. Objects that are moving kind of in a parabolic motion through projectile motion, as we'll see in lab, objects that move in that manner, they move with motion that's horizontal and vertical, but they're independent of one another. So another way to think of it is that the acceleration due to gravity is the only acceleration it's experiencing. Its weight force is the only force it's experiencing, and that's straight down. So if we, again, we're assuming we ignore air resistance, and ignoring air resistance, it's going to only coast horizontally, maintaining a constant horizontal speed, while vertically it's falling in the same way that we saw with throwing a ball straight up and down. So again, if you have a ball that's moving through a parabolic motion like this, you can really think of that as being a ball that's moving straight up and coming straight back down while also moving horizontally. So if I put these two motions together in one motion, you get the parabolic shape that you'll see here. Okay? So again, this ball, as it goes up, its horizontal velocity, the distance over time it's covering in the horizontal direction, that stays constant. It's constantly moving to the right at the same rate the whole time, but vertically, it's actually slowing down, coming to a stop, and then falling. All right, so again, we're talking this type of motion, parabolic motion. If you notice, it coasts sideways, decelerates on the way up, and then accelerates on the way down in the vertical direction. So that is the idea behind projectile motion or parabolic motion. So if you were to throw a ball or launch a ball with a cannon or something, I guess you'd launch a cannonball, not a ball. Anyway, if you were to launch an object and you wanted it to go the maximum possible distance, my wife's laughing at my weird discussion about cannonballs. Anyway, if you wanted something to go the maximum possible distance, what angle should you launch it at? What if you wanted to go the maximum possible height? What angle would you launch it at? Well, to give you the maximum range, the maximum horizontal distance, you'd want to launch it, as you may have guessed, at a 45-degree angle. If you launch it at a steeper angle, it will go higher, but not as far horizontally. If you launch it at a lower angle, it will have a lot of horizontal speed, but it won't have enough height to go any further than at 45 degrees. Now, if you wanted it to go as high as possible, that's a little bit of a trick question. You just launch it at 90 degrees straight up, so all the velocity goes to height, but then you better get out of the way because it's going to come back down when you launched it. So here's a really quite tricky example for you all. This really is going to take kind of the math side of what we're doing in this class to the extreme as much as possible. But I wanted to challenge you with trying this kind of problem, and you're going to get to try this type of question as a challenge question on the extra credit in class on Friday as well. So here you have somebody who's shooting a paintball. They're going to shoot it horizontally, so straight horizontally, so it's not moving up or down at all when they shoot it, and they're going to shoot it at 75 meters per second. And the height that they're holding their paintball gun is 1.5 meters off the ground. So two questions for you. One is, how long is the paintball in the air? And the second is, where will the paintball land? How far away from the shooter will it land, assuming that you missed the target? Okay, so I want you to pause the video right now, and I want you to try to solve this using those two equations of motion I gave you in class. So pause it and give it a go. All right, so hopefully you've tried this out. Now this is pretty tricky, right? Because really those equations that I gave you, as we've talked about, you can use those for looking at things that are moving horizontally or things that are moving vertically. And we've used it multiple times for things moving vertically, like the flea example in class and in lab, right? So now here you have something that's moving horizontally and vertically. But again, you can just use those two by themselves because you have this paintball that's being launched sideways, but it's really moving both falling vertically and being shot horizontally. The cool thing here is in the first part, part A, when it asks you how long is it in the air, that's just the same amount of time as it'd be in the air if I were just dropping it. If I was dropping it straight down from 1.5 meters high, the time would be the same because it's not having any vertical velocity at the beginning. It's not moving up or down at the very beginning. Okay, so we're going to start by trying to figure out the time using the vertical motion, treating it as if it's just something we're dropping from 1.5 meters high. All right, so the first thing we need to do with these types of questions is figure out which of those variables we know. So look, this is all of our variables from the two equations. We're starting from initial y height of 1.5 meters off the ground, and it's going to end at a height of 0 meters off the ground because it's hitting the ground. The acceleration we know is gravity, but down, so negative 9.8. We don't know how fast it's moving as it impacts the ground, but we don't care because we don't need it in that first equation I gave, or excuse me, the second equation I gave you. And the initial velocity, it's the same as if we're just dropping it because it's being shot perfectly horizontally, so it has 0 initial y velocity. It's not moving up or down at all at the beginning, and so time is the only thing we need to figure out. So to do this, we're going to use the equation I gave you in class. The final position equals the initial position plus the initial velocity times time plus 1/2 the acceleration times time. Now we know the initial position is 1.5 meters. We know the final position is 0. The initial velocity is 0. And then 1/2 acceleration times time. So the only thing we really don't know in here is time. We know that the initial position is 1.5. I moved it to the other side of my equation, so it became negative, if you're wondering where that negative sign came from. And that equals 1/2 the acceleration, which is negative g, times time squared. So to solve for this, I multiply both sides by 2, so then I get 2 times negative y initial, and then I divide by my acceleration to put it on the other side. And since you have time squared, to get rid of the squared, as you guys have told me before, you take the square root of both sides. So the time equals the square root of 2 times our height divided by gravity, but the height is negative because it's falling down and the gravity is also negative. And so the time it takes to reach the ground is a box-worthy 0.553 seconds. So that's how long it's in the air. You shoot it perfectly horizontally, and it takes that long for it to drop, the exact same as if you just dropped a ball 1.5 meters above the ground. So the second question asks you then, how far horizontally away from you does it land? Now we can follow the exact same process. Now we're looking in the horizontal direction, so our initial position is 0. Our final position is what we're trying to find. There's no acceleration in the x direction. We're ignoring air resistance, so there's no force, nothing to slow it down. So it's going to stay at 75 meters per second the whole time. That's what it starts at. As we're told in the problem, that's what it's going to end at because it stays the same. And now we know the amount of time it goes for. So we can use the same equation once again. Now for the x direction. But since the acceleration is 0 and the initial x position is 0, we just get distance equals rate, the velocity, times time. So the distance it covers is just 75 times the amount of time, 0.533 seconds, and you get 41.5 meters. Huh, I just noticed I have a typo. This should be 0.553, not 0.533. But 0.553 times 75 does give you 41.5 meters. So that is a box-worthy answer, but this is a typo. That should be a 5. Sorry about that. Cool. So that just wraps up the end of our motion. We're actually going to do that projectile motion stuff more in the extra credit on Friday, as well as in the workshop, in the lab next week. But now I want to introduce you guys to the next section where we look at the physics behind ramps. So as you think about ramps, right, they're nice. They make it easier to move things. I don't know if you've helped somebody move, but I have multiple times and moved myself. And the ramp on the back of the truck is great, right? It makes it much easier to lift a heavy object. To grab something like a refrigerator, lift it vertically and place it into the back of a truck, super difficult. But you can gradually roll it up a shallow ramp and it becomes much, much easier. I wonder what physics is at play. What about that makes it so much easier? When is it easier? When is it harder? These are things that I wonder how we can describe with physics. I know if it's a really shallow ramp, it makes my life a lot easier. If it's a really steep ramp, it feels the same as if I'm just lifting the thing up. So the angle of the ramp must matter. I wonder how. Here are the 4 questions we're going to be tackling, partly in this video and a little bit in class on Monday. So I want you to pause the video and maybe just think about these. Grab your roommate or a friend or somebody and discuss these questions with them, or just talk to yourself. I like to talk to myself about physics all the time. So pause it and give it a go. Are you pausing? Look here, I'll take a drink of my Dutch Bros here while you think about it. Okay, so let's go ahead and dive into these one at a time. First one is, if you're using a ramp, maybe you're pushing a cart up a ramp. In this case, apparently I have a shopping cart. My first question is, why does that cart not fall through the floor? Why does the ramp even support it? Or just in general, look here, I have a ball sitting on my hand. Why is the ball sitting on my hand and not falling through? Well, it kind of seems silly, right? Well, my hand was in the way, right? Well, really what's happening is the ball and my hand are both made up of matter and atoms, and those atoms are not able to occupy the exact same space. So as gravity's pulling down on the ball and forcing those atoms to interact with the atoms in my hand and molecules, all of a sudden they're not able to occupy the same space, and so as a result my hand ends up pushing up on the ball. So there's an upward supporting force that we oftentimes refer to as the normal force working against the ball. And so we call this support force that's always perpendicular. It's always normal is another word for perpendicular in math, right? It's always perpendicular to the surface of contact. And so we call that the normal force. So the weight of the cart is down and that normal force is up. And if it's sitting on a flat surface, stationary, the normal force and the weight force are equal. Okay, so as I put the ball on my hand, the ball is pushing down on my hand equal to its weight, and my hand is pushing up equal and opposite. All right, the second question is, why does the floor exactly support the cart? Why is it exactly equal to the weight? Why not more? Why not less? Well, in short, it's really because the floor is kind of lazy, right? It's only going to support as much as it has to. Okay, so it's not going to, imagine, what if it were to push up more than the weight? Well, if it's pushing up more than the weight, that means there'd be a net force on the ball upward and you just magically start jumping off of my hand. That's not going to happen. That's not practical. It doesn't make sense. And it's because, really, again, a result of this interaction at the molecular level, that we get a normal force that's exactly equal and opposite to the ball's weight. And at times, they're not perfectly equal. Like when I first put this down onto my hand, that's a bad example. It's easier to see it if you like drop it onto a flat surface or something. So like if I were to drop it on my desk here, you can kind of see how it bounces up and down over and over again. So the first time it impacts, the force is actually more than the weight, which results in it bouncing up. And then it becomes less because it's not in contact. Then it hits and it's more, and it keeps bouncing up and down, losing a little bit of energy each time until it's perfectly at equilibrium. Okay, so things in general will come to rest and be in a state known as equilibrium. As the name implies, everything is equal, all the forces are equal, so therefore there's no net force when it's in equilibrium. So again, it bounces up and down a little bit and eventually reaches equilibrium. It's very obvious with my tennis ball, less obvious with something like a cart. When you set the cart on the ground, you don't watch it bounce up and down, but at a very, very small scale, it does oscillate, moving back and forth just a little bit, which is kind of weird to think about. So once it's in equilibrium, the net force is 0, so the weight force down is exactly equal and opposite to the normal force going upward. So here's an interesting question. If you walk up to your friend and you push them, does your friend push you back, yes or no? Can you, like, say somebody comes up and tries to push you, is there a way to avoid pushing them backwards? Or do you even push them at all? What does that even mean, right? What do you think? Well, the correct answer is no. If you push a friend, inevitably they're going to push you back. This might sound weird, but it's true. This is actually the idea known as Newton's third law of motion that tells you for every action force, there's an equal and opposite reaction force. So if I go over here and I lean and push on the wall is pushing back on me. And this is easy to see actually. Right now I'm in a rolly chair. If I push on the wall, I actually move backwards because the wall is pushing back on me, equal and opposite. Our forces, the force I push to the wall is going to be equal and opposite to the force it pushes back on me, in the same way that you have an equal force with the ball resting on my hand. So for every force, there's an equal and opposite reaction force. That's why I have this picture here of a person kicking a soccer ball. It's an easy place to see this idea. When you kick a ball, the ball really is kicking you back just as hard. And you can feel that, right? If you don't believe me, try kicking something like a bowling ball or the wall. You'll definitely feel it then, right? Or I remember I used to play, as a kid, we kind of invented this game we called backyard baseball, where we took these kind of smallish basketballs and we'd hit them with big bats in the backyard. And because we were small, weak kids, you couldn't hit it that far, so it was like hard to hit it out of the yard and stuff. And you'd run around and throw the balls at each other and just be kids. But really, what we were doing is experiencing Newton's third law. Because a lot of times when you hit that heavy basketball with the bat would like bounce backwards because it has an equal and opposite reaction force on your bat as it bounces backwards. All right, so that's Newton's third law of motion. I found a pretty cool video to help drive this point home. Since we're not in class and I don't get to do all kinds of demos, this is a crazy physics professor doing a sweet demonstration of Newton's third law. All right, so what he does is he takes here this fire extinguisher. So as he pulls the trigger on the fire extinguisher, it's going to shoot gas out one side. And watch what happens to him as it does that. There's a force of the exhaust coming out one way, and it pushes him backwards with an equal and opposite force in the other direction. Newton's third law of motion. This is, believe it or not, what you just saw right here, that's how a lot of spaceships work. They shoot gas out one way, which pushes them back the opposite direction. Pretty cool, right? So here's another question. If you push or pull, however you want to do it, on a friend who's moving away from you, how will the force you exert compare with the force of your friend? So now that they're moving, will that make your friend push harder, or you will push harder, or will they still be the same? What do you think? Try it out. Try pushing something that's moving. See what happens. Well, a lot of you will be like, oh, they're not pushing you back very much at all because they're moving away, right? But the answer is they're actually equal. It just becomes harder for you to push them when you're pushing a moving target. But the force, Newton's third law, doesn't like take a break when something's moving. It's always the case. The forces between two contact surfaces are always equal and opposite to one another. All right, so again, I push the wall, it pushes back on me. All right, you kick a ball, it kicks you back just as hard. So there's a common misconception here. So a lot of people are like, okay, so if this is the case, if like two cars hit and the force is equal and opposite, don't those forces just cancel out? Like, why do the cars get all banged up when this happens? It seems like they should just cancel each other out all the time. And no, the trick is the forces are equal and opposite to one another, but one force is on one car and the other force is on the other. So they're each experiencing their own force. It's just the magnitude of those forces are equal. Okay? Another misconception that people sometimes have. You think about this, and I'm talking about cars, and you're like, wait a second. I've seen a car accident or a picture of a car accident where there's like a big truck, super large, heavy, or even a semi, and like a tiny little sedan. They collide, and the truck looks fine, and the sedan looks smashed and all beat up. Why is that? If they're experiencing the same force, why don't they both get beat up the same? Well, the key is to think about all that we've learned. What about Newton's second law of motion, right? Newton's second law tells us that net force equals mass times acceleration, right? So it's about the overall, the net force acting equals mass times acceleration. If they both have the same force, the truck has a big mass, so this is big, right? Big mass, apparently upward arrow means big. So its acceleration is smaller, all right? So if I were to write this, let's try this, writing this a slightly different way here. So like if we think about for the truck, you have the force for the truck is going to be equal to, it has a big mass, and therefore its acceleration is smaller. The force on the car, the sedan, is the same amount of force. Try to draw my F's the same size. Same amount of force, but since it has a smaller mass, it needs a bigger acceleration to compensate for it. And it's this large acceleration that makes it so much more dangerous for the people riding in that smaller car, whereas the smaller acceleration means less whiplash and less damage in the bigger truck. So tricky, right? Physics, you got to think about the whole picture, how it all comes together. You can't just look at individual pieces. Looking at individual pieces without the big picture leads to misconceptions. All right, so the next question is, why is it so easy to push a cart up a ramp? Why is that even helpful? And the answer is, well, because, as we're just talking about, the ramp, it's supporting part of the weight. So when you're pushing a cart up the ramp, you only have to push part of its weight, not the whole thing. Think about it. If there's an object sitting on a ramp like this, if its weight's going straight down, there's a normal force that's perpendicular to the surface, right? And so since the normal force is perpendicular to the surface, it's going to support a chunk of the weight. Not all of it. A little bit of the weight is still going to be down the ramp, but part of the weight is into the ramp. So if you notice, I'm thinking, remember we talked about vectors. Forces are vectors. I'm taking my weight and thinking about it as being two different forces. One that's into the ramp and one that's down the ramp. The part into the ramp is supported by the normal force, and then the part down the ramp is the only part that you have to oppose to push it up. So you can think about this. If this thing has a total weight, of let's say 1,000 newtons, the ramp portion of that could be over 900 newtons. So you only have to support a little over 100 newtons. Okay, so it depends on how it's broken down, how the forces are going to be, how strong each force is going to be, and that will determine how much you need to support. But it's based on the steepness of the ramp. The steeper the ramp, the more of the weight that's down the ramp. The shallower, the more that's supported by the ramp. Okay, so again, the net force on the cart, the only thing not being supported is this ramp force, which is not very strong. So if you want to push something up the ramp, you only have to overcome the ramp force, which is cool, right? So if you got a big refrigerator and you put on a ramp, the ramp supports most of the weight of the fridge, and you just have to push up to overtake or overcome the little bit that's left over. So here's a question for you. If I were to push uphill on a ramp just hard enough, so exactly equal to that downward ramp force, what would happen to the cart? So again, we have my trusty ball. Okay, I put it on a slope here. If I push exactly equal to that portion of the ball's weight that makes it want to roll down my hand, it's ramp force, right? If I push exactly equal to that, what's going to happen? Will the ball be motionless? Will it move at a constant velocity? Will it accelerate downhill, or will it accelerate uphill? What do you think? Well, the correct answer is, if you're pushing exactly equal, net force is zero, Newton's first law, which means the object, if it's in motion, will continue to stay in motion at a constant velocity. And if it's at rest, it will stay at rest. So it could be motionless, but the most correct answer is answer B, that it has a constant velocity, and that constant velocity could be zero, in which case it would be motionless. So thinking about this some more, if you want to start getting something going up a ramp, when you first want it to move, you have to push harder than the ramp force because you need it to accelerate upwards. But you only need it to accelerate a little bit just to get it going. Once you get it going up, then you can decrease your force to be exactly equal to the ramp force, and then you move it up at a nice constant rate. If you stay larger than the ramp force the whole time, you're just going to accelerate and get going faster and faster as you go, and then the refrigerator goes flying into the back of the moving truck and it smashes your dining room table or whatever's in there, right? It could be crazy. So you push harder just at the beginning to accelerate it a little bit. Once it's at a nice safe speed, you decrease how hard you're pushing to be just exactly equal to the ramp force. And then when you get to the top, you actually decrease your force to less than the ramp force so that it slows down. So the net force is actually down the ramp, causing it to slow down. So you push harder, it accelerates up the ramp, you decrease, keep it at a constant velocity, during which the net force is 0. Then at the top, you decrease even more so that the net force is down and it slows to a stop. So basically what you're doing is you're using one of the many forms of what's known as mechanical advantage. You're using basically a simple device, a ramp, to give you mechanical advantage, to help use the physics of the world around us to make your life easier. All right, so you're using mechanical advantage through the ramp to make your life easier so you can do less force to get an object moving, but you have to apply that less force over a greater distance. So like again, if I have my tennis ball and I just want to take it and lift it up to this height, I have to push hard on it. Okay, it's not that hard because it's a tennis ball, but you know, let's say I get something a little heavier. Here's a mass, right? This is what, 250 grams. To lift this thing, all right, I got to push hard, but I only have to move it this far. The other option would be to put it on a ramp and gradually slide it up, taking it over a much larger distance, but when you push it over a larger distance, you don't have to apply quite as much force. So you are using mechanical advantage. So this gives rise to a concept of a new topic that I wanted to introduce with this whole video. So all of this is in many ways leading up to this idea. So what does that mean? So if I'm taking this and I'm lifting it straight up, or if I'm putting it on a ramp here, okay, here's my keyboard ramp, and sliding it up the ramp, all right, there's a physical quantity, a part of nature that's actually independent of which way I go. So whether I start with it down here and lift it straight up, or start with it on the ramp and gradually slide it all the way up the ramp, there's one thing that's the same regardless of how I do it. Anybody know what it is? Well, if you did the reading, you should know that this concept is what's known as work. So the amount of work it takes to get this weight here from the ground. So again, here, let's put the camera down a little bit so you can see on my desk. Oh, down a little further apparently. So here's my tennis ball. We'll stick with the tennis ball. Okay, if I want to get the tennis ball from the bottom of the screen down here to the top of the screen, whether I lift it straight up like this or whether I gradually roll it up this slope, I'm doing the exact same amount of work either way. Now if I lift it straight up, it's a harder force, but I do it over a shorter distance. When I push it up the ramp, it's a much easier, lesser force, but it's covering a much greater distance. All right, so the work you do is the same either way, but the amount of force is different as well as the distance. And so what we find is that work is defined as being equal to the force applied to an object multiplied by the distance over which that force is applied. So you have to make sure that your force and your distance are in the exact same direction. All right? So what this means is if you have a really steep slope, you have a smaller force over a larger distance. And if you have a shallower slope, you have a smaller force over a larger distance. But in both cases, the work is the exact same, provided the box is starting at the same height and ending at the same height. So again, you see here the shorter distance and the longer distance. So the question then is, all right, work is force times distance, but why do we care? What is work? Well, work is directly related to energy. So I want to talk for a minute about energy and work and then unpack this a lot more throughout all of the year, actually, all of the semester, but a lot more on Monday especially. But work and energy are directly related. Energy is the amount of kind of like potential or possibility stored up in something, all right? And it's actually a conserved quantity. So it is constantly changing forms from one to another, but it's never actually able to be created or destroyed. It's just constantly changing, all right? And really, you can also think of energy as the potential to do work. So again, if I have my ball, all right, my muscles have a certain amount of energy in it, the potential to do work, and so I can push this ball up, and I'm transferring energy from my body into the ball, and now the ball has energy when it's up here. It has the potential to do work, and if I let it go, it's going to do some work. Well, really, gravity is going to do work on the ball by causing it to roll down the slope. So work and energy are really directly related. Work is how energy transfers or moves, And energy is the amount of potential something has to do work. And there's energy all over the place. So if you think about, right, like you put gasoline in your car, that gasoline has energy stored within it, chemical energy. And when you release or harness or burn the fuel to release that energy, then you're releasing its capacity to do work, and it does work by pushing your car forward. All right, so you're using the energy in the gas to do work to move your car, and then your car then has energy of motion known as kinetic energy. And so we constantly see work and energy interrelated all the time. As energy is changing forms, work is being used to move it from one type to another or to transfer it from one object to another. I do work on the ball to move it up. All right, there we go. It now has energy that gravity can then do work on it as it pulls it back down. So it's constantly, energy is always changing forms. And we're going to talk about this more in class on Monday. The last thing I want to do is just do an example for you of using this equation of work equals force times distance. But before we do the example, just so you're aware, we're talking about units here. Work is force, which is units of newtons. We're multiplying that by units of meters, which is for distance. And so we get 1 Newton multiplied by 1 meter. When it's in the same direction like this, you get 1 joule. So joules are the units we use for work and for energy. All right, so here's the last example problem I'm going to finish up with before calling it a day. So here you decide you're working on a farm, you live on a farm, you have a wood-burning stove that wants to use the energy of chemical potential energy inside the wood. You want to burn it to warm up your house. So turn it from wood, stored chemical energy, into heat energy in your house. You want to burn it, but you need to get the wood to your house. So you got a wood pile that's 150 meters away from your back door. You strap it to your fancy little tractor here, and you pull it on its little sled from wherever the wood pile is to the back of the house. So I tell you that you pull this thing and the tractor does 35,000 joules of work during this time. My question to you all then is, if that's the case, what is the average force acting on the wood pile from the tractor? So assume it's pulling straight. There's actually an angle, so the force would actually be a little different than what we're going to calculate. But let's assume it's pulling straight. If it does this much work over this much distance, what is the average force? Pause it and try to calculate it. Well, hopefully you did the calculation, but we know that work equals force times distance. And in this case, we're told the work and the distance. And so force, if we divide both sides by distance, should just be equal to work divided by distance. So the force should just be the 35,000 joules divided by the 150 meters, or as we plug in our values, we should find that the force is 233 newtons, which is, once again, box worthy. So that's a lot of new information here to think about when we're talking about Newton's third law, equal and opposite forces, right? And then this idea of work and energy, which can be a little bit confusing, but it's one of my favorite concepts in all of physics. This idea that the energy, all the energy that God created at the beginning of time in the universe has been here since he created the universe, and it's just constantly changing forms, and we use work to describe how it's changing between different forms. Super, super cool idea. So we're going to unpack that more next week. Hope that helps us stay on track and get pumped for class on Friday with Neil, and I'll see you all on Monday. Have a box-worthy day.